So today we're going to talk about impulse. We are still in the energy and momentum unit. Let's go ahead and take a look at our notes sheet and follow along. So I have a discussion question for you. So we have a cannon with a cannonball inside. For the same force, why is the speed of a cannonball greater when it's shot from a cannon with a longer barrel? Let's pause the video and take a moment to think about that first. Okay, now that you've had a moment to think about why the speed of the cannonball would be greater when it's shot from a longer barrel, let's discuss. You'll notice that the cannon itself has a longer barrel, which means it has a larger distance for the cannonball to travel. So if it has a larger distance for the cannonball to travel, if it's given the same amount of force, it has a longer period of time in which it can increase its speed. So that means that given the same amount of force, the cannon with the longer barrel is going to have a cannonball that leaves the cannon with a higher velocity because it had a longer time to increase its speed. So impulse is a force acting for a period of time. We called work was a force acting over a distance. Let's take a look at this tennis ball and the racket. When we watch the tennis ball, let's slow it down a little bit. When we watch the tennis ball, as it makes contact with the racket, you'll notice that the tennis ball actually deforms and the racket itself moves back a little bit. What this is showing is that the tennis ball is in contact with the racket for a certain period of time. And we all know when we hit a tennis ball with a racket, it's in contact with the racket for a very small amount of time. So that gives the tennis ball a large force. So force and time are inversely proportional to one another. If we decrease the amount of time, we must be increasing the force, and vice versa. So here's another discussion question for you. If we have a raw egg and we throw it as hard as possible at a wall, we know that it's going to break. But what will happen if it is thrown just as hard, so same amount of force, at a loose bed sheet? Do you think A, it will break, B, it won't break, C, it might break, depends on the thrower, D, breaking eggs is wasteful and we shouldn't do it? And to follow up with a challenge question if you have a little extra time, is there a greater impulse on the egg when it is thrown at the wall or the bed sheet? Let's take a minute to think about our answers for both of those. Now that we've had a moment to think about it, let's go see what happens. Let's watch that one more time. When that egg is thrown at the bed sheet, it doesn't crack. But why? What's different about the egg being thrown at a bed sheet than the egg at a wall? Well, the egg at a wall, the egg is in contact with the wall for a much shorter time period, so it has a much greater force, which causes it to break or crack. When the egg is thrown at the sheet, it's in contact with the sheet for a much longer time period before it comes to rest, which means it has a much smaller force. And for that challenge question, because F and T are inversely proportional to one another, they actually have the same impulse. Since time was a lot smaller for the wall, the force was a lot greater. And the time was a lot larger for the sheet, the force was a lot smaller. The impulse itself did not change. Here's another question for you to think about. You are sitting at a baseball game when a foul ball comes in your direction. You prepare to catch it barehanded. To catch it safely, you should do what? Should you A, move your hands towards the ball, B, hold your hands still, C, move your hands in the same direction as the moving ball, D, jump so that your feet are not in contact with the ground, or E, lower your center of mass by crouching? Let's Let's take a moment to think about that. Hopefully you thought that, C, you should move your hands in the same direction as the ball. Because if we move our hands in the same direction as the ball, we increase the time in which the ball is in contact with our hands and the time that it takes for the ball to come to rest. So it's going to hurt our hands a whole lot less, meaning there's a whole lot less force from the ball in our hands. So C is the correct answer for that one. Let's go through a couple of examples in which we see that impulse is present. Airbags, bumpers, boxing gloves, and I'm going to show a short video. So let's start with airbags. As you watch the dummy hit the airbag, you'll notice that the dummy is in contact with the airbag for quite a long period of time. If that airbag wasn't present, he would be in contact with the dashboard in a much smaller time, which means that the force is a whole lot less when he's in contact with the airbag than when he's in contact with the dashboard. So the purpose of airbags is to reduce the amount of force that we feel when we get in a car accident. Same thing with seatbelts. It takes a longer time period to come to rest if you are moving at a high velocity than it would if you didn't have a seatbelt on. It wouldn't take you as long to come to rest. You would hit that dashboard or the airbag a lot quicker. So we have two different examples here, the airbag and the seatbelt, both showing us impulse. We're increasing the time in order to decrease the amount of force. Let's take a look at bumpers. Okay, you can see that when these two cars are crash tested against one another, that their bumpers are moving in toward the center of the car. So the bumpers that are flimsier actually, and not as strong, create a larger amount of time of impact before the two cars come to rest. So since the bumpers cause a larger amount of time to occur between the cars moving and coming to rest, it results in a lot less force. If those two bumpers were old school bumpers on cars from the 60s, they wouldn't crunch as much as you notice they crunch in this video, which actually would result in a lot more fatalities than there are today with our cars that are built the way they are. Boxing gloves, well, let's just think about that one. If you were to be hit by someone that had a pair of boxing gloves on, it would hurt a whole lot less than if you were hit with someone that didn't have boxing gloves on. And the reason this is because the time of impact is increased for the person wearing boxing gloves. So you're going to feel a lot less force. So once again, we're seeing this force and time inversely proportional to one another. Let's see another one, a wrecking ball. So we've all seen or heard of a wrecking ball. Wrecking balls are used to demolish buildings. And in this video, an H&R Block ad, we have a wrecking ball that is wrapped with a stuffed bunny. And when this wrecking ball bunny hits the wall, you'll notice it doesn't demolish the building. Even though the same wrecking ball that would normally demolish that building is inside of the bunny, it doesn't demolish the building. The reason why is because the bunny, with the wrecking ball inside, is in contact with the wall for a lot larger time period before it comes to rest, which means it has a lot smaller force. If this bunny were not on the wrecking ball and it was just a wrecking ball, it wouldn't take as much time for that wrecking ball to come to rest. It would hit the wall and result in a large force, demolishing the wall. Once again, impulse. All right, so let's take a look at the derivation. Let's start with F equals ma. We started talking about this with the first discussion question, with the cannonball inside the longer cannon having a larger velocity as it leaves. And the reason, even if it had the same force, the reason why it had a larger velocity was because it had a longer amount of time to increase its speed. Let's break this down a little bit. We know that acceleration is actually the change in velocity in a given time period, so delta v over t. If we go ahead and multiply t on both sides of our equation, we'll notice that the t on the right-hand side cancels out because t divided by t is just 1. So we're left with t times F equals m times delta v, which is really time times force equals mass times the change in velocity. We're going to rename these two quantities. T times F is impulse, and mass times change in velocity is momentum, which we'll be getting into next time. But let's go ahead and define both of these. Impulse, we're going to use the variable I. I is equal to F times T. That's our new equation. Force is F, has the units of newtons, capital N. Time has the units of seconds. So therefore, impulse has the unit of newton second. Momentum, P, is equal to mass, m, times change in velocity, delta v. Mass has the unit of kilogram, velocity has the units meters per second, and momentum has the units kilogram meters per second. Let's take a look at an example. We have a 2,000 kilogram car starting from rest at a red light. The driver holds down the gas pedal for 10 seconds, applying an average force of 375 newtons. What is the impulse on the car? Well, let's first write down what we know. Our givens are the force is 375 newtons, the mass is 2,000 kilograms, and the time is 10 seconds. And we're looking for impulse, that's our unknown. We know an equation for impulse, it's equal to force times time. So therefore, impulse is equal to 375 newtons times 10 seconds, which results in 3,750 newton seconds. Let's take a look at some force time graphs. Real forces in life are not constant. For example, the egg thrown at the wall isn't in contact with the wall for a large amount of time, but it does have a large force. So you can see the force is spread out over that short time period. And the egg thrown at a bedsheet is in contact with the bedsheet for a larger amount of time, resulting in a lot less force overall. But if we were to find the area under the curve of each of those curves, we would notice that they're the same amount of area, which means it's the same amount of impulse, because impulse is equal to force times time. And area under each of those curves is force times time, impulse. So same area for both means that it has the same change in momentum and impulse for both eggs thrown at the wall and the bedsheet. Although the egg thrown at a wall is squeezed into a shorter time, results in a big force, and the egg breaks. The egg thrown at a bedsheet is spread out over a longer time, smaller force, the egg survives. So here, you practice one. If we have a bare fist hitting someone and a boxing glove hitting someone, what should the force time graphs look like? Well, the bare fist is in contact with the face for a short amount of time, larger force. The boxing glove is in contact with the face for a larger amount of time, smaller force. Same impulse for both. So let's practice that. Example 2. Suppose a force acting on a tennis ball is representative in the graph. Estimate the impulse on the ball. We know that the impulse is the area under the curve of a force time graph. Okay? Well, step 1, figure out how much one of the boxes is worth. If we know from 0 to 0.01 seconds, there's 1, 2, 3, 4, 5 boxes. Each one of those boxes is worth 0.01 divided by 5 seconds. Same thing with the y-axis. There is 2 boxes between 0 and 100, so 100 divided by 2 would be the y dimension of the box, which results in 50 for the y and 0.002 for the x. Now we need to know the area of that box. The area of the box is the base times height, since it's a rectangle, which results in 0.1 Newton seconds. So each box is worth 0.1 Newton seconds. Now we need to figure out how many boxes there are. Well, let's count them. 1, 2, 3, 4, 5, 6, 7. And then we can count these ones as halves, just about. Those two added together makes a whole. These two added together makes a whole. And these four kind of add together make 1, which we get a total of 12. Step 3, final step, let's multiply the number of boxes by each area of each box. So 0.1 Newton seconds was the area of one box, times 12 boxes gives us an impulse of 1.2 Newton seconds. So here's a discussion question for you to try. A car engine applies an increasing force to a car for a certain amount of time as seen on the graph below. What is the impulse on the car during the first 3 seconds? Go ahead and try it on your own first. We can see that the area under this curve from 0 to 3 seconds is a triangle. So we need to know the area equation of a triangle. We know that area of a triangle is 1/2 base times height. Next thing we would need is the base, which is 3 seconds, the height, which is 20 newtons. So 1/2 times 3 seconds times 20 newtons results in 30 Newton seconds. C. One last demo to finish us off. I call this the happy ball, sad ball demo.
Hi guys, so we've been talking recently about impulse and momentum. So I have a little demonstration for you today, but before I do the demo I need to set the scenario for you. So let's say it's on a Saturday morning and you wake up and it's early and you hear your whole family up and about in your house and all you want to do is go back to sleep. But you notice that your door is cracked open. So you're thinking to yourself, how can I shut that door without having to get out of bed? So you look over at your nightstand and you notice that you have 2 things on your nightstand. You have a tennis ball and you have a clay wad. There's a difference between these 2 different objects. One of them, your tennis ball, bounces. Your clay wad does not. Okay, so you have to decide. You only get, let's say you only get 1 chance. You can throw one of the 2 objects at your door. Which one would you throw at your door to shut it and why? Keep in mind, let's keep a couple things constant. They both have the same mass and they're both the same size around. So you got a big clay wad because that's about the size of a tennis ball and it's going to be the same mass as the tennis ball. So think about why and then we'll do the demo. Now that you've had a chance to think about which of the 2 objects, the clay ball or the tennis ball, would close the door and why, let's see which one works. Let's start with the clay ball first. Let's make sure that's the clay ball. So this is going to simulate our door. This is a 2x4 and if it knocks over, that's our door shutting. If it doesn't knock over, you've just hit your door but you didn't quite shut it. So we have a ramp, we're keeping things constant. Both of the 2 different objects are going to start at the same height. I'm going to release both of them from rest. Okay, clay ball did not knock it down. Let's put the clay ball back. And let's do the tennis ball. So the clay ball only hit it 1 time. So if this bounces off of the door, our 2x4, which simulates the door, I'm going to catch it so it doesn't hit again because we only want it to hit once, just like the clay ball did, keeping things constant. I don't think that one was quite right. Let's try that again. Sure enough, it knocks it down. And let's do it one more time just to prove. Let's set it up in the same exact position. Clay ball. Does not knock it down. Tennis ball. It's our happy ball. Knocks it down. So let's think about why. Why did the the tennis ball work. And we're going to call this one our happy ball because it bounces and our sad ball because it doesn't. So try to come up with a scenario, and maybe a drawing will help you explain using impulse and momentum as to why the happy ball knocked the door down or closed the door and the sad ball does not.